The ICEVI, the Nippon Foundation Mathematics Package for Teachers video series, Abacus as a Mathematical Tool. Title of the video, Square Root of 6-digit numbers involving 4 zeros as lower digits. Example, 100 and 20,000. In using 5-digit numbers involving zeros at the end, we demonstrated that the square root may be a perfect one or one with the decimals too. For example, the number 96,100 having 2 zeros at the end gives a perfect square root, 361. Whereas the number 53,600 having 2 zeros at the end is not giving a perfect square root, and the exact square root is 231.52. Let us use the example 120,000 with 4 zeros at the end and demonstrate that it is not a perfect square. That means it does not give a perfect square root. Let us use this number 120,000 by leaving 3 columns in the right extreme of the abacus. That is, first 0 in the 4th column, second 0 to its left, third 0 to its left, and 4th 0 to the left of the third 0, and 2 to the left of the 4th 0, and 1 to the left of 2. For the purpose of calculation, let us consider the groups as 12, 0, 0 and 0, 0. Take the first group, 12, and consider the perfect squares there. 4 and 9 are the perfect squares. Now, 9 is the highest perfect square, and therefore take the square root 3. Set 3 to the immediate left of the number 1 and subtract 9 from 12, which is giving 3 as the remainder. Now you are left with 30,000, as we have to leave the last 3 columns for the decimal part, and therefore 3 followed by 4 places which have zeros. In the next stage, double the number 3, which is the square root, and set 6 in the extreme left of the abacus. Now consider 30 of 300, the first 3 digits of the remaining number. Ask how many 6's in 30. You get the answer as 5, as it is giving a quotient without a remainder. It is safe to reduce 1 and consider 4 as the assumed quotient. In the case of small numbers, you need not have to go for an assumed quotient. Here, set the number 4 to the right of the first digit of the square root 3 and to the right of the number 6 in the extreme left of the abacus. Now multiply 4 with the 64, that is 24. That should be subtracted from 30, which gives the remaining number as 60. Now 4 multiplied by 4, which is 16, should be subtracted from 60, and that gives 44. Now we are left with 4400. So whenever you have 0 at the end of the number, you always use the 3 columns earmarked for the decimal part and take the remaining columns as the ones having 0. Now look at the square root. It is 34. Now this should be doubled, and therefore clear 64, and in that place you have to set the 68. Now consider 68 and 4400. Look at the first two digits of the dividend and the divisor. How many sixes in 44? By saying 7, reduce 1 for safety and set the 6 to the right of the square root 34 and to the right of the number 68. Multiply 6 with 686 and subtract that from 4400. The multiplied value of 6 multiplied by 686 becomes 4116, and when you subtract this from 4400 you get the remainder as 284. Now you have a remainder 284 after this stage of calculation. That clearly indicates that 120,000 is not a perfect square. One may tend to assume that having even numbers of zeros at the end of the number may give a perfect square, but it is not true. We mentioned repeatedly that in the case of any number of zeros of an even digit number is not going to be a perfect square, and this is a classic example. If you want to have the decimal digits of the square root, you can carry on as per the procedures explained in the previous exercises. The purpose of this exercise is just to show that having an even number of zeros of an even digit number can never be a perfect square. Let us take up some more numbers involving zeros at the end.